Okay, section 4.7, inverse trig functions. Before we actually start talking about inverse trig functions, I want to remind you about just regular inverse functions. Back in chapter 1 we talked about, and I want to use an example like y equals x cubed. If we want to talk about the inverse function of y equals x cubed, to find that inverse function, we switch the places of x and y, and then we solve for y, which would give us y equals the cubed root of x. So y equals x cubed and y equals the cubed root of x are inverse functions from one another. And here's what that means is I can look at the graph of y equals x cubed, okay, which is my standard cubic function, and then I can look at the graph of y equals the cubed root of x, which is the standard cubed root function, which looks kind of like this. And what happens is that these, since they're inverses of each other, will give us something that reflects across the line y equals x. Okay, and use your imagination a little bit there, because obviously that graph is not fantastic. The other thing that it means is that if I know x and y values for my original function, like if I plug in 2, I get 8 because I cube it and I get 8, or if I plug in 3, I get 27. Well, if I plug in values for the inverse function, I get basically my x and my y switched around from the first function. For example, if I make x 8, I get 2 for y. If I make x 27, I take the cube root of that and I get 3. Okay, so inverse functions are basically when we take x and y and we flip it around. One thing we talked about when we did inverse functions was we said if our original function passes the horizontal line test, that means that our inverse of that is also a function. Okay, so if we talk about, so now let's talk about if I have the inverse of sine. Okay, first off, if I have y equals sine x, and I want to switch my x and my y around, well, how in the world do I solve that for y? What we do is we introduce a new notation, basically, and we say this is y equals the inverse sine of x. So that button on your calculator with sine of -1, that's where this comes in. Y equals the inverse sine of x. The other way we can say it is to use the term arc sine. Okay, and here's a couple things we need to know is, first off, if I graph y equals sine x, just a standard graph where my period is 2 pi. Okay, that's kind of a really bad graph, but bear with me. Okay, this does not pass the horizontal line test, not even close. Like, because this is a periodic function, it just keeps on not passing the horizontal line test. So right now, as I have it, this is not actually a function. But if I restrict my domain to something like this, okay, which basically this is pi over 2, and this is negative pi over 2. Okay, then what I get, if I just look at that part, is something I can take the inverse of. The inverse of that, if I graph it, okay, first off, my y values become my x values. My x values become my y values. Okay, and so then if I reflect that graph across the line y equals x, I get what looks kind of like this. Okay, I get something that looks like that. What this is actually saying, the inverse sine function, is it's going to give me things like sine of -1 of 1/2. And what we're really asking is, at what angle is sine 1/2? Okay, and our answer has to be between negative pi over 2 and pi over 2. Okay, and it has to be between there because that's the only place that the inverse sine function is actually defined. Okay, is between negative pi over 2 and pi over 2. So let's do some examples of this. Example 1, evaluating without a calculator. Find the exact value of each expression without a calculator. That means there has to be something special about what we're doing. Like we can use the unit circle or special right triangles or something like that. Otherwise, we couldn't do it without a calculator. So part A is basically what I talked about on the previous slide. And so what we're saying is, what is the angle whenever sine is 1/2? Well, sine is opposite over hypotenuse. So this is if I want to use special right triangles. I'd make a special right triangle that meets the requirement that sine is 1/2. And then I'd say, what is the angle that is shown there? And across from 1, remember, is the angle 30 degrees. And so that means that the answer to this is pi over 6. Then we might think about, hey, is that between pi over 2 and negative pi over 2? Yes, because it's in the first quadrant. On part B, the inverse sine of negative square root of 3 over 2. Now remember, we're only talking about from negative pi over 2 to pi over 2, which means that I can't have my triangle B in these two quadrants. It's just not going to be there. So that means that the only place I can have a negative square root of 3 for my opposite side is right here. 2 right there, 1 right there. So what is this angle? Well, across from square root of 3 would be 60 degrees, which is pi over 3. And it's negative because it's going the wrong way. So it would be negative pi over 3. That's the same angle as, what, 5 pi over, no, not 5 pi. Yeah, 5 pi over 3. Okay, that's the same angle as 5 pi over 3 if we were going the positive direction, but because my range of values is between negative pi over 2 and pi over 2, negative pi over 3 would be the answer that I'm looking for. Okay, so part C, all of our values that we plug in for x, like this is the inverse sine of x, all of our x values have to be between negative 1 and 1. That's the domain of our function, okay, because that's the range of sine whenever we restrict it so that it can have its so it can have an inverse function. If that didn't make much sense, then just ignore it. Okay, but basically my point is this number has to be between negative 1 and 1, and pi over 2 is like 1.7-ish, and that's not between 1 and negative 1. So this does not exist. Like, I can't even talk about what the inverse sine of pi over 2 is. One thing to clue you in is if they ever try to put like an angle in where the inverse sine of where we're doing the inverse sine, there's a good chance it doesn't exist. Not necessarily, but it's a pretty good chance. So on part D, it says the inverse sine of pi over 9. Well, let's think about this. Pi over 9 gives me a triangle right here. Okay, a triangle that I don't know the sides of. But the inverse sine of that triangle is the angle it takes to get there. Well, what angle does it take to get there? Well, it takes pi over 9 to get there. So I'm going to rewrite that because that's kind of hard to read. So that equals pi over 9. Okay, so basically our inverse sine and our sine kind of work like they're canceling each other out, kind of, okay? So let's look at E, so you understand what I mean by kind of. I have 5 pi over 6 for sine, which is an angle over here. Okay, that this angle to get around is 5 pi over 6. But I want the inverse sine of that, okay, which according to D would mean I would pick 5 pi over 6, but that's not actually in my domain, right? So what really happens is that I'm going to say, well, what is this reference angle here? That reference angle is pi over 6. So if you have something that doesn't end up giving us an answer, like if I pretend like I can just cancel these out, 5 pi over 6 is not in the range of the inverse sine, so it can't be the answer, but I can pick the reference angle 4/5 pi over 6, which is pi over 6, and that would be my answer. Example 2. Now if I evaluate this with a calculator, it says put it in radian mode, so that's pretty important, and then evaluate these inverse sine values. So what you're going to do is you're going to type second, or you're going to press the second button, and then the sine button, and then you're going to type in negative 0.81, and you're going to press enter, and that decimal is negative 0.944. Okay, and that's our answer. Simple as that, right? If I want to do part B, the inverse sine, so that's second sine, and then I want to press sine again, and then I want to put in 3.49 pi. What that's going to look like is it's going to say on your calculator the inverse sine of sine 3.49 pi, and then you can close the parentheses if you want. So it looks just like what the problem was. So if I press enter on that, then that gives me negative 1.539. Okay, so evaluating with the calculator, pretty stinking easy. Just make sure you're in radian mode for it unless it specifies for you to put it in degree mode. Alright, now let's do inverse cosine and tangent. Okay, so inverse cosine, if we think about regular cosine and we think about its graph, okay, we start at the top and then we make it back up to the top, so halfway we're down at the bottom. It looks like this. So we need to pick out basically a range of values so that this will pass the horizontal line test. And the range of values we're going to pick is this box right here. Okay, because if we go past that box either direction, we start getting repetitive values. Well, this point right here is pi, which means that cosine goes from 0 to pi. Now, if we draw the inverse function of this, then, okay, my range for cosine is from -1 to 1, which means my domain for my inverse cosine is -1 to 1, because they switch places. My domain that I'm restricting myself to for regular cosine is from 0 to pi, and so that's my new range here. And this is what my graph is going to kind of look like. Is this kind of situation, something like that. You can look in your book for better pictures because it's not real fantastic. But you get the basic gist. The point of this is that our answers for inverse cosine are going to be between 0 and pi. Okay, so in this case, we're restricting ourselves to the first and second quadrant instead of the first and fourth quadrant. So make sure you remember that whenever you're working them out. Basically, cosine is the one that's different, because if I graph tangent, okay, my asymptotes are really helpful, because if I just look at one period of tangent, that passes the horizontal line test. So I'm restricting tangent to be between negative pi over 2 and 2. Pi over 2, I mean. Negative pi over 2 to positive pi over 2. This inverse function, I have 1 and -1, which that's really, those points don't actually really matter. What matters is that this is pi over 2 and negative pi over 2. And if I reflect this across the line, y equals x, I get something that looks like this. Okay, so I actually can end up with values bigger than 1 and less than -1, where I couldn't with sine and cosine. Okay, but for tangent, just like sine, we're going to only look in the first and fourth quadrants for these. So let's do some. Find the exact value without a calculator. The inverse cosine of -√2 over 2. Okay, well, where does negative square root of 2 over 2 happen for cosine? That's a triangle over here, or if we look at the unit circle, that's over here. Okay, and what does that mean this angle is to get around to here? Because remember, it's okay for it to be in the first and second quadrant for cosine. The angle to get around to there is 3 pi over 4. Okay, because the angle inside is pi over 4, because it's a 45, 45, 90 triangle. So the inverse cosine of negative square root of 2 over 2 is 3 pi over 4. Part B, tangent of the square root of 3. Well, first off, let's remember tangent is opposite over adjacent, so this is really square root of 3 over 1, so that gives me a triangle, square root of 3, 1, 2. What is that angle that's inside? It'd be 60 degrees, which is the same thing as pi over 3. So the inverse tangent of the square root of 3 is pi over 3. Now, part C says the inverse cosine of negative 1.1. Well, let's think about that. What we've said before is that the inverse cosine of cosine, that those kind of cancel each other out, right? And so what we can do is we can draw an angle for negative 1.1. And so this is kind of weird to think about because we're used to thinking of these in pi's, right? But if we think about them as decimals, negative 3.14 would be over here. This would be like negative 1.7. So negative 1.1 is somewhere in this quadrant. It gives us this triangle. So what we're trying to do is figure out what the angle inside that triangle is. Well, doesn't it take 1.1 radians to get to there because we just drew an angle that was negative 1.1? So this is going to equal positive 1.1 because the inverse cosine cannot be in the fourth quadrant. So we're talking about what is the reference angle, basically, that is involved in cosine of negative 1.1. The reference angle is 1.1, so that's our answer. Okay, let's look at a few more examples, because what if we, have weird things going on, or what if we combine different trig functions? How does that work? So part A says, what is the cosine of the inverse sine of 1/2? So we would start in the middle to get a triangle and then work backwards. So the inverse sine of 1/2 gives me a triangle where my opposite side is 1, my hypotenuse is 2. It's a special right triangle, so the other side is square root of 3. I'm trying to figure out what is the cosine of this triangle. Well, the cosine of this triangle is the square root of 3 over 2. So it didn't matter that I didn't actually find the angle, because what I actually wanted was cosine of whatever that angle is, and I had the triangle already, so I could just figure it out. I could have said, hey, that's pi over 6, and then found cosine of pi over 6. That works too. But I didn't have to do it that way. I could just look at the triangle. Let's look at B, cosine of negative 1 of cosine of 7 pi over 4. Let's think about where 7 pi over 4 is. 8 pi over 4 would be all the way around. So this is actually just pi over 4 short. Gives me a special right triangle of 1, 1 square root of 2. And so if I'm taking the inverse cosine of that, I'm trying to figure out what angle is the reference angle of that triangle. Well, this angle inside would be 45 degrees, which is pi over 4. So that would be my answer. Part C, arc sine of cosine of pi over 3. Well, let's figure out what cosine of pi over 3 is. It is 60 degrees, so that's a triangle right here. Remember that arc sine is just the same as inverse sine. I'm trying to figure out what is the angle of this triangle. The angle of this triangle would be 60 degrees, which is pi over 3 in radians. Okay, so that would be our answer. And that's what we've got going on for 4.7.